Welcome to This Explainer. Today, we're diving into something that's, well, highly complex, but absolutely crucial for all of us to understand. We're talking about a hidden, practically indestructible danger that's quietly lurking in our global food supply right now. Think of it as a microscopic villain, one that food safety scientists literally go to battle with every single day just to keep it off your plate. So, what do peanuts, your everyday pantry spices, a glass of raw milk, and, yeah, even your morning cup of decaf coffee all have in common? I mean, on the surface, absolutely nothing, right? But if we zoom into the world of molecular biology and food safety, they actually share a very specific, kind of terrifying vulnerability. They are all prime targets for this invisible enemy we're unpacking today. Okay, let's dive into this. Here's our roadmap. 1. Meet the invisible threat. 2. Where do they hide? 3. High stakes for human health. 4. The global defense system. And 5. Detecting the undetectable. Don't worry if the science sounds heavy, we'll break it all down clearly. Section 1. Meet the invisible threat. To really get a grip on this, we're going straight to the source. We're looking at an actual internal food safety brief from Nestlé. Now, this isn't some flashy marketing brochure. No, this is the hardcore, incredibly strict scientific standard that guides one of the largest food companies on the planet. Peeking under the hood of documents like this gives us a direct, unfiltered look at the immense scientific rigor required to keep global food supply chains safe. And the specific contaminant this brief focuses on, aflatoxins. So what exactly are aflatoxins anyway? Well, they're mycotoxins, basically toxic compounds produced primarily by two types of mold from the Aspergillus species, specifically Aspergillus flavus and Aspergillus parasiticus. There are a few main types you should know about: B1, B2, G1, and G2. Now, out of all these, aflatoxin B1 is the heavy hitter. It's considered the most toxic and usually the most common. And hey, do you know why they're called B and G? It's actually a super fascinating bit of lab science. It's based on how they glow under ultraviolet light. B stands for blue and G stands for green-yellow. Pretty cool, right? Oh, and there's one more crucial type listed, M1. The M stands for milk. That's because M1 is a metabolite that forms when animals eat feed contaminated with the B1 toxin, and yep, it ends up right in their milk. Now here is where this turns into a massive logistical nightmare. 237 to 299 degrees Celsius. That's roughly 458 to 570 degrees Fahrenheit. That insanely high number is the melting point of aflatoxins, and it's the exact temperature required just to get them to decompose. I really want you to let that sink in for a second. Water boils at a mere 100 degrees Celsius. Standard cooking, baking, even most heavy-duty industrial food processing, they don't even come close to destroying this molecule. It is physically incredibly resilient. Section 2. Where do they hide? So, where are these things lurking? Well, the fungus that produces aflatoxins absolutely thrives in specific environments. The contamination rate is heavily dependent on temperature, humidity, and soil conditions during harvest, transport, and storage. And the most vulnerable, high-risk foods? They're things we literally eat every day. Peanuts, nuts, maize, cereals, spices like chili and nutmeg, and dried fruits like figs. Interestingly, data from the EU between 2000 and 2006 showed that historically, contamination was exceptionally high in Brazil nuts and pistachios compared to other crops. And what makes this even trickier is that contamination is highly heterogeneous. That's a fancy way of saying it clusters in these highly toxic little pockets rather than spreading evenly, making it remarkably difficult to sample and actually find. Now, what's really interesting about this is you'd probably think all coffee is treated equally by fungi, right? Well, actually, no. The safety brief notes that aflatoxin levels are generally low or even non-existent in regular coffee for one brilliant reason: caffeine. Yeah, caffeine actually inhibits aflatoxin production. It acts like this natural fungal deterrent. But if you remove the caffeine to make decaf coffee and then happen to store those beans improperly in humid conditions, that decaf can actually harbor substantially higher aflatoxin levels. It's just a perfect example of how incredibly complex food chemistry really is. Which naturally leads to the big question you're probably asking yourself right now. If it's in our raw food, and we know it's this incredibly tough, can't we just cook it out? I mean, can't we just destroy it in the kitchen or the factory before we eat it? Well, the answer is kind of a mixed bag. Take milk, for example. Remember that M1 metabolite we talked about? Unfortunately, standard pasteurization or even full sterilization completely fails to destroy AFM1 in milk.
It survives the whole heating process entirely. But on the flip side, consider a contaminated oil seed, like a peanut or a sunflower seed. If you crush it to make vegetable oil, the harsh industrial refining process used to make that crude oil ready for us to eat actually completely destroys the aflatoxins. So refined oil is totally safe, while raw milk requires incredibly strict preventative monitoring right from the start.
Section 3. High stakes for human health. We have to talk about why scientists take this so seriously. Aflatoxins are classified as genotoxic carcinogens. That is a terrifying term, but what it means is they are chemical agents that actively damage the genetic information, the literal DNA within a cell. This causes mutations that can lead to cancer, primarily liver cancer. And here is the absolutely critical scientific point. According to current paradigms, genotoxicity does not have a threshold dose below which zero adverse effects occur. Basically, any exposure carries some risk. Because of that, health authorities literally cannot establish a safe intake value. Their goal, it's simply to get exposure as close to absolute zero as physically possible. But it's not just about long-term cancer risks. There's also acute toxicity known as aflatoxicosis. It's rare, but when people consume highly contaminated food over a really short period, it causes massive immediate liver damage. How bad is it? Well, in severe cases, it can take up to 10 full years for a body to recover. A follow-up study noted in the brief found that is exactly how long it took survivors to fully heal. 10 years. It really highlights just how profoundly potent this molecule is.
And this brilliantly illustrates a major global challenge, one based heavily on dietary habits and geography. In Europe, the estimated daily maximum intake of aflatoxins is incredibly low. We're talking around 2.25 nanograms per kilogram of body weight per day. But in parts of Africa and Southeast Asia, that estimated daily intake can reach up to 200 nanograms. That is a massive, massive geographic exposure gap. And it's driven heavily by climate, since the fungus loves hot, humid environments, but also by stark differences in agricultural drying techniques and storage infrastructure.
Section 4. The Global Defense System. Okay, let's relieve a little tension here and talk about how we're protected. European Union regulations are a fantastic example of a tiered defense system. For groundnuts, like peanuts, that will be subjected to sorting and physical treatment later on, the allowable limit of the B1 toxin is 8 micrograms per kilogram. But if those nuts are going straight into a bag for direct human consumption, that limit drops dramatically to just 2. They effectively force the supply chain to clean up the product. And for milk? The M1 limit in raw milk is just 0.05. But for infant formula, it is a microscopic 0.025. Because children are far more vulnerable to liver toxicity, regulators enforce a near-zero tolerance policy to protect them. Section 5. Detecting the undetectable. So how do they actually enforce these strict laws? Well, laboratories rely on incredibly advanced microscopic testing methods. We're talking things like high-performance liquid chromatography, ELISA screening, and solution fluorometry. These machines have limits of quantification as low as 0.05 micrograms per liter. To put that into perspective, we're talking about finding parts per trillion of a toxin. It is literally the equivalent of finding a single specific drop of water in an Olympic-sized swimming pool. This is the invisible science working behind the scenes, making sure everything from your morning coffee to cattle feed is safe. We've explored the microscopic chemistry, the hiding spots, the severe health stakes, and our highly advanced defense systems. But consider this for a second. Aflatoxin production is fundamentally driven by heat and humidity. So as global climates shift, as temperatures rise, and weather patterns alter, the map of where this fungus thrives is going to change. The big question is, how will our global agricultural practices and our invisible defense systems adapt to keep our future food supply safe in a warming world? It's a massive challenge for the next generation of food scientists. Thank you so much for joining me for this explainer. And keep asking the big questions.